Have you ever stopped to think about what's really going on inside your phone or your computer or, well, pretty much any gadget you own? Today, we are pulling back the curtain on a tiny, unsung hero that makes almost all of modern electronics possible, the diode.
So here's how we're going to break it down. First, we'll get a hacks as a protector and how it tames the power from your wall. And finally, we'll look at some specialist diodes that do things that are basically electronic magic.
Well, let's take a look at how this one simple trick acts as an invisible bodyguard for your gadgets in ways you probably rely on every single day.
I mean, think about it. Emergency lights in a building, or critical computer systems in a hospital. They absolutely cannot afford to lose power for even a fraction of a second. So how do they switch over instantly? Well, the secret is a cleverly placed diode.
Here's how that works. As long as the main power from the wall is on, the diode just sits there, blocking the path from the battery. This is great, because it keeps the battery from draining. But the instant the main power cuts out, that block vanishes. The diode immediately opens the gate for the battery, and the power takes over seamlessly. The lights don't even flicker. It's brilliant.
And here's another way it protects your stuff. We've all done this, right? You're in a hurry, you put the batteries in backward. Without a diode, that could literally fry the electronics. But with the diode in there, it acts like a bouncer at a club. You got the batteries in the right way? The correct polarity? Yep, you're on the list. Come on in. Put them in backward. Sorry, the diode blocks the entrance. No current flows, no damage done. It's so simple, but it's genius.
All right, now we get to what is probably the diode's most important job, taking that chaotic, wild power from your wall outlet and turning it into the calm, stable power that your electronics actually need to survive.
See, the power coming out of your wall is, well, it's kind of a mess. It's called alternating current, or AC, because it's constantly flipping direction, back and forth, 60 times a second. Now that's great for sending power over long distances to your house, but it would absolutely destroy sensitive electronics. Your phone, your TV. They need a calm, steady, one-way flow of power called direct current, or DC. So how do we tame that wild AC? The process is called rectification, and it's where diodes really shine. The simplest way is to use one diode to just chop off the entire backward-flowing half of the current. That works, but you're wasting half the power. The really clever solution uses a team of 4 diodes in what's called a bridge diode. They work together to grab that backward-flowing current and actually flip it around so that all of the power is flowing in the right direction. Now this gives you a bumpy DC current. So for the final step, we add a capacitor, which acts like a shock absorber for electricity, smoothing out all those bumps into a much more stable, usable DC voltage. Now, even after all that smoothing, there's usually a tiny bit of that original AC bumpiness left over. We call that ripple voltage. And for really sensitive stuff, like a high-end stereo system or a precise lab instrument, the whole goal is to get that ripple as close to zero as possible. It's the difference between crystal clear sound and that annoying low hum you sometimes hear.
Of course, just like you wouldn't use a garden hose to put out a forest fire, not all diodes are created equal. They have specific ratings for how much current they can handle flowing forward, and how much voltage they can block when it's trying to go in reverse. So you've got your common 1N4001 for small electronics projects, all the way up to a beast like the MR754 that's built for heavy-duty power supplies. You got to pick the right tool for the job.
Okay, so we've seen how diodes can switch and rectify. That's their day job. But now let's look at the specialists, the diodes that have some truly incredible superpowers that have completely revolutionized technology.
So what happens when the problem isn't that the current is alternating, but that your DC power source is just messy and unstable? It's jumping all over the place. How do you get a rock-solid, precise voltage from a source like that?
For this job, we need a specialist, the Zener diode. And this is where things get a little weird, because the Zener is designed to work backward. A normal diode just blocks reverse voltage, but a Zener is specially built to conduct or break down at one very specific reverse voltage, let's say 5.1 volts. If the voltage tries to climb any higher than that, the Zener opens up just enough to shunt the extra energy away, clamping the output at a perfect 5.1 volts. It's basically a pressure relief valve for electricity.
How does it do this? Well, what's happening at the atomic level is pretty wild. There are 2 main ways. For lower voltages, a powerful electric field literally just pulls electrons free. For higher voltages, it's more like a chain reaction, where one high-speed electron slams into an atom and knocks other electrons loose in a controlled avalanche. But either way, the end result is the same, a super stable, regulated voltage.
So, when electricity flows through a regular diode, it creates a little bit of waste energy in the form of heat. The diode gets a little warm. But decades ago, some very clever engineers asked a world-changing question. What if we could design a diode that released that energy not as heat, but as light? That one question led to one of the most important inventions of the last century.
And that, of course, is the magic behind the light-emitting diode, or LED. Now, creating white light is a really cool trick. A powerful little blue LED chip shines onto a thin layer of yellow phosphor. The phosphor absorbs some of that blue light and spits it back out as yellow light. When the leftover blue light mixes with that new yellow light, our brains perceive the combination as pure white. It's an incredibly efficient process, and it's why LEDs have pretty much taken over all of lighting.
And here's the kicker. This whole process works in reverse. A photodiode is basically an LED that sees light instead of making it. When light hits it, it generates a tiny electrical current, perfect for things like the light meter in your camera. So, what if you took that idea and made that photodiode really, really big? Well, then you'd have a solar cell. A solar panel is really just a giant diode that's been optimized to take the energy from sunlight and convert it directly into useful electricity.
So just think about that for a second. We started with a simple rule, a one-way street for electricity. And from that single, simple idea, we get automatic backup power, protection for our gadgets, clean DC voltage from the wall, super stable power supplies, and even the ability to turn electricity into light, and light right back into electricity. The humble diode really proves that sometimes the most powerful and world-changing inventions are the ones that are based on the simplest rules.